Awesome.
Here we go.
Thank you. You're the best. Okay. Awesome. Let's start presenting. Is that working? Oh, no, that's too much. Is that good? Good lighting? Okay, let's get started. Welcome to the exam review, guys. Hope you're not too stressed, but this is gonna be good. It's gonna help you study, help you review. So yeah, let's get started. So exam 2, it's gonna have 20 multiple choice questions, and they're all gonna be worth 3 points each. There's only gonna be 4 free response questions this time, so less free response. But altogether, total, those 4 are gonna be worth 40 points. I know, yeah, but it's okay, because there's only 4 of them. There's a 3-hour time limit on this exam. I don't think most people end up using those full 3 hours, so hopefully you don't either. You can. You totally can if you want to. You don't have to. So it opens tomorrow and it closes on Monday. Just be aware that it closes, doors close at the testing center at 6 on Monday. So if you're planning on like studying all day and then going in at 8 and just taking it until the testing center closes, you've already missed it. So just remember that. I've definitely done that before. In the exam, you will be given a periodic table, an equation sheet, the 105 equation sheet, and then the electronegativity table is what I've been told. So you should be able to do the polar bond stuff pretty easy. Okay, any questions about the format, logistics? Okay, we're chilling. Okay, study material. So this is obviously a study material, but it's not all the study materials you have. There are tons of super helpful study materials on Learning Suite. You have the practice exam. There's some practice questions that some TAs have made. Wasn't me. You have the slides. I'm going to post these slides. On YouTube, you have the OChem Tutor, Khan Academy, Dr. Sansom. They're all YouTube-y people. You have your own notes. If you took notes, I never take notes. You have the class presentations that she gave. Lots of study materials. Practice exam. I think I already said that one. But yeah, hopefully this will help you prepare. Okay, so we're going to go over we're going to go over the study guide. So basically this PowerPoint is pretty much point for point what's on the study guide. So that should be pretty helpful. So first we're going to be talking about bonding. We're going to be talking about types of bonds, and then we're going to be talking about valence bond theory and molecular orbital theory. We're going to start off with the hardest stuff because we're ready and we're motivated. We're going to crush our spirits first and then go to the other stuff. So let's talk about types of bonds. We have ionic, covalent, and metallic. Ionic bonds, this is basically stuff you need to know. Last exam you had like on the free response, you had to like write definitions and stuff. And you were supposed to know the definitions and like the buzzwords. So as long as you know what's up here, you should be fine if it asks you what these are, right? So ionic bonds are like really, really, really big difference in electronegativity. So the electron in one atom is transferred to the other, and then it's kind of just like magnets. Covalent is sharing the electrons, and then metallic is just weird. It's pretty much like a C. All the metals act as kind of one big atom, and the electrons go everywhere. Kind of weird. Yeah, any questions about types of bonds? Okay, let's go on. In these bonds, the covalent and ionic bonds, there's electronegativity differences. And I've been looking online, and there's a lot of different ranges for when it starts being polar, when it starts being ionic and not covalent anymore. What you should know is that the ranges are 0.4 and 1.8. If it's anything less than 0.4, it's going to be non-polar covalent. If it's between a difference of electronegativity of 0.4 and 1.8, it's going to be polar covalent. And if it's bigger than 1.8, the difference, it's going to be ionic. Yeah. I'm sorry, what? Exactly 0.4 is yes. I think exactly 0.4 is nonpolar. But I don't think they're going to give you anything that's exactly 0.4. I don't think carbon hydrogen, I think that's less than 0.4. Unless it's exactly 0.4, unless. Okay, carbon hydrogen, that's 0.4. If it's 0.4 or less, it's nonpolar. Thank you. So yeah, does that make sense what we have up here on the board? Yeah, let's go on. Okay, let's talk about lattice energy. Does anyone know what lattice energy is? That's how I remember it. It's kind of funny. Okay, well, lattice energy is when you have atoms and they come together in gas form. It's the energy released when 1 mole of an ionic, I'm just reading it. The energy released when 1 mole of an ionic compound forms from its free ions in the gas phase. So you don't really need to know what it is, but you do need to know how to calculate what has bigger lattice energy and what has smaller lattice energy. Okay. So you should have done some practice problems with lattice energy. But the big thing you want to have in your mind when you see a problem that asks about lattice energy is you want to think about Coulomb's law. That's what it's called. So the electrostatic force, this is Coulomb's law. You don't have to memorize it, but it would be good to know, just conceptually, is equal to charge of atom 1 times charge of atom 2 over the distance between the nuclei. Okay, so we can take this and we can think about, let's just think about these ionic molecules that we have here. We have calcium sulfide or beryllium sulfide. Which one do you guys think has the greater lattice energy? Okay, Isaac says calcium sulfide. Why would it be calcium sulfide? If it is calcium sulfide, why would that have greater lattice energy? Yeah, right. Because calcium and what is Ba? I don't know. Barium have the same charge. We don't need to worry about charge. And so does sulfur. What we need to worry about is size in this one. And calcium is smaller than barium. So this distance is going to be smaller, dividing by a smaller number. Force is going to be bigger. Yeah. And it's the same thing. Actually, which is a greater lattice energy? Calcium sulfide or calcium oxide? Calcium oxide, because it's smaller. Oxygen is smaller. What about lithium fluoride or sodium fluoride? Very good. Very good. There's a practice problem on the practice exam that has you rank electronegativity or the lattice energy of like 4 different ionic compounds. And it gives you, I think the ones it gives you are like MgF2, or Isaac, what were the other ones? Luke, what were we doing? There's KF, NAF. Sorry, spoilers for the practice exam, but this is good to go over so you know it. And you could just forget about it and do the practice exam and learn it again. And calcium, okay, calcium. And the question wants you to rank these from least to highest lattice energy. So this is let's do a practice problem. All right, work with your teammates or do it with your own if you want to. But try to find out of these 4, which has just rank them lowest to highest. Ready, set, go. You guys see the board? Can you see it? Yeah. Oh, sorry. size trumps, or charge trumps size. So look at the charge differences, and then look at the size. I know, I realize that it's still on. I just don't really know how to turn it off. So. Okay, who needs more time? Are we feeling pretty good about it? Okay, what do you guys think is lowest to highest lattice energy on this ranking? What's the lowest? This one? Yeah, okay, we'll do KF. That's the lowest. What's the next lowest? NaF. Why is sodium fluoride higher in lattice energy than potassium fluoride? Na is smaller than potassium. That's right. What's next? What has more lattice energy than those? Calcium fluoride. Right? And then obviously the last one. So I did say this when you guys were doing the problem. That's my bad. But you guys want to look at charge first, right? Charge kind of trumps size when we're talking about lattice energy. So calcium and magnesium have a charge of +2. And there's 2 fluorine atoms, and they're both -1, so it's going to be -2. So it's going to be 2 times 2 over whatever the distance between the nuclei is, right? So these are automatically, just because they have more charge, going to be higher in lattice energy. And then we could look at size to determine between the two, which one has more, which one has less. Okay, any questions about lattice energy? Yeah. 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 Well, yeah, charge. Right. When they're all the same, because these are all fluorine, I would look at the charge of the cation instead of the charge of the anion. So this one is +2, this one is +2, whereas these ones are just +1, right? So look at those. This does matter. I don't know. You can think of it that way too, but cation helps me. So yeah. Any other questions? Yeah. Yeah. Magnitude of the charge. Let's move on. Let's talk about valence bond theory. So you guys went over valence bond theory in your recitations. Hopefully it wasn't too confusing, but we're going to go over it again because it's important to know. So valence bond theory, pretty much, it's this theory that allows us to focus on individual bonds in the molecules, and it relates this bonding to the orbitals in the molecule. And we talked a lot about, a couple weeks ago, or maybe last week, about shapes, like tetrahedral, trigonal, bipyramidal, or whatever. This is a theory that kind of takes advantage of those shapes and builds off of it. So you should know what it does and what it doesn't do. And we're going to do the same thing with molecular orbitals, what it does and what it doesn't do. And you have to know the strengths and the weaknesses of both. Be able to compare them. There's going to be like multiple choice questions that say, what is molecular orbital theory better at than valence bond theory? So the cons of valence bond theory is it doesn't predict bond energies, and it can't describe electron distributions in the molecule. So paramagnetism or diamagnetism. It's also just not really what happens. That's a pretty big con, but it does help us. It helps us understand the shape of the molecule. It's helpful. Okay. Any questions about before we get into it? Okay. Talk about sigma bonds. So sigma bonds are single bonds. Sigma single. So sigma bonds in valence bond theory is an overlap of orbitals between the nuclei. I don't know why it says can be with hybridized orbitals. It's usually always hybridized orbitals. I guess unless you have like 2 H's, H2 is just S and S. But yeah, usually it's with these hybridized orbitals. So you can see these shapes that we were talking about, right? This is tetrahedral right here. sp3, right? Because there's 4 groups. sp2, 3, 4 of them. There's trigonal bipyramidal right there. And there's octahedral right there. And we can get more into that, but does sigma bonds make sense for everybody with valence bond theory? Okay. Remember that in valence bond theory, sigma bonds are overlaps of orbital. Okay. And this is what I was talking about with the electron groups and valence bond theories. It's just the shapes, right? You use the shapes to determine the hybridization of the molecules. Okay, so if you have a tetrahedral thing, like let's say NH3, which is going to be N single bonded to 3 hydrogens and then a lone pair. Can everyone envision that in their mind? That's going to be tetrahedral. It's going to have sp3 hybridization, right? Same thing with CH4. Same thing with H2O. They're all tetrahedral electron geometry. Now, they're not all tetrahedral molecular geometry, but electron geometry helps us determine the hybridization. Yeah. Yeah. You guys got to memorize this chart. Yeah, so it sucks, but you do have to memorize it. You have to memorize the bond angles, which isn't that bad because there's only like 4 different numbers, and there's patterns. Like they're pretty simple. Yeah. Valence bond theory helps us determine molecular geometry through the hybridization of the individual molecules. Or atoms, sorry, not molecules, individual atoms. Yeah. No, this one would be more than, right here. Oh, down one more. This one? Oh, this one? No, because it's, I think that's just saying it's way less. I think you'll be fine if you just have one. You should just be fine. But if you want to do 2, that's cool too. 3 is pushing it, I'll mark you down. I'm just kidding. Yeah. Steric number 2. Yeah, you can also use steric number. No, I don't. You can use either one. As long as you know how to do it using one way, you're totally good. Okay, any more questions? Should we go on? Okay, let's talk about pi bonds. So it's not pi. So pi bonds, we talked about how sigma bonds were, I'm going to erase Coulomb's law. Sorry, Coulomb. Great law, but we're done with Coulomb's law. So we talked about how sigma bonds, C single bonded to C. This is a little C here. This is a little C. It's just, oh boy, that's bad. Let's try again. An overlap of orbitals, right? This is the sigma bond right here. And it's along the internuclear axis. Whereas pi orbitals, you can see here, are above and below the internuclear axis. And they happen when there's a singly filled p orbital or just orbitals that are not hybridized. So let's say you have sp, right? P2, even better. You have an sp2 hybridized carbon bond. So that looks like this. It looks like C double bonded to C. We'll throw some H's on there. These carbons, the hybridization is sp2 on both of them. Yeah? That means we've used, each carbon has an s orbital and 3 p orbitals, right? That means we've used 1, 2, 3, sp2. We have 1 p orbital that's non-hybridized. Or unhybridized, I should say. So I drew this out in our recitation. We're going to draw it again. So p orbitals, pi bonds are when the p orbitals kind of just overlap with each other. Pi bond, and that's a single pi bond, right? Even though you have 2 places where it connects, it's a single pi bond. If you had a triple bond, ignore the H's, you'd have one coming out. You'd have a p orbital coming out and going into the board, and that would also be connecting. That would be another pi bond. Yeah. But yeah, it's the whole cloud. So they're there too. And it's not going to look like this. It's more going to look like But yeah, pretty much. Okay. Any questions with pi bonds? Did I explain it okay? Is anyone confused? Yeah, electron density, the electron cloud. Yeah. Well, we know that carbon, because of where it is, we learned last unit, the orbitals. We know it's got 1 2s valence orbital and 3 2p valence orbitals. We're just looking at the valence orbitals here. So we use these orbitals and we use 1 orbital for every electron group around it. This C here, we're taking it back down to just a double bond. How many electron groups does it have around it? 3, right? So we're going to use 3 of these valence orbitals to hybridize together to get 3 hybridized orbitals. sp2. Does that make sense? And we have 1 p left over, and that's just kind of chilling. It's unhybridized. That can be used for pi bonds. Can we move on? I'll put my remote. Okay, let's talk about some important things when we're talking about these hybrid orbitals. These are some important ideas, and I'm just going to read them, and we can explain them or go into more detail. But when we're talking about these hybrid orbitals, you could think that they just exist. They don't exist. They don't exist when the atom is by itself, right? If you just have a single carbon atom floating along, you don't have any hybridized orbitals. You just have the 3p orbitals and the 1s orbital. Those are the valence orbitals, right? You have the 2s and the 2p orbital. Just chilling. This only happens when you have some sort of bonding going on. It kind of helps, stabilizes, makes it easy. Does that make sense? Okay. The next thing is that hybrid orbitals are, you get them from combining atomic orbitals. So it's always going to be equal. If you put in 3 atomic orbitals, like an s, a p, and a p, you're going to get 3 sp2 hybridized orbitals. That makes sense, right? 3 for 3. Okay. All the orbitals in that sp3, all 3 of those are going to be the same shape. They're going to be the same energy. They're going to be going in different directions. And sp2 is trigonal planar, right? And that makes sense because it's 3. We learned the geometry. That makes sense. We talked about that second to last one. It's just dependent. You can use the electron geometry to help you figure out the hybridized orbitals. And then we just talked about this last one. Does anyone have any questions about any of these things? Anything not making sense? Yeah, can we go on? Almost. Okay. Oh, look at that. Dang it, I put the answer on there. Oh, good. Cover it with my hand. Okay, well, I was going to have you do the practice problem. Oh, well, I put the answer on there. There's no one look. So I was going to make it a practice problem, and I was just going to have describe the bonding in C2H4. And I was going to have you, actually, let's do it. Ready? You got a hint. You got some hints. But we're going to do a practice problem, split up with your people or whatever you want to do, and describe the bonding in C2H4. If anyone has any questions, I can come over to you. Okay, who needs more time to work through this problem? We'll give you like 30 more seconds. Okay, let's talk about this problem. So when you're given a problem like this, and it says describe the bonding in C2H4, it's probably going to give you more words than this. But basically, this is what you're going to do. First, you're going to want to draw the Lewis structure for C2H4, right? Then you're going to want to draw out the valence sigma bonds, right? So using your knowledge that both of the C atoms are trigonal planar, you're going to know they're both sp3. So you're going to draw the sp3 with the H's. The H's are just S, right? Because the only valence orbital that they have is S. And they can't hybridize just in S, so it just stays S. So the C's overlap with the S, and then the C's overlap with each other. So you have 5 sigma bonds. And then what's left is the unhybridized p orbitals. Those form a pi bond. And you're just going to describe what's going on like I have here. Does that make sense? Yeah. Yeah. Yeah, I think so. I did when I had to take this exam. But it's really not that hard. I mean, we're all not artists. I mean, maybe some of us are artists, but none of the TAs are artists. So trust me, we're gonna understand. But if you just do something like this, it's not that hard. You got it, I believe. And it could be way worse than that. And you'll get points. But you should be able to draw it just so that we know you know what's going on. Yeah. I would. Yeah. Just so that you understand what's happening with the pi bond. Because I think what happened last time was a lot of people knew the answers, but to the questions that were being asked in the free response, but they didn't give enough words to indicate that they knew. So even though they got the right answer, they didn't have the explanations. So you just want to make sure that you're really kind of teaching the graders why, if that makes sense. Not really teaching, but kind of explaining in detail. Yeah. Did you have a question? No? Yeah. I didn't draw the pi orbital. I'm lazy. I can. Any other questions? Yeah. Yeah. Yeah, this is just one pi bond. Both of these things together are just one pi bond. This is the double bond right there. Any other questions? Okay, let's talk about molecular orbital theory. Let's do it. So this one is different. This one, instead of looking at individual bonds between atoms, it looks at the whole molecule. And what it does, this is what it does well. it describes all the molecular properties, the energy spectra, the polarity, the charge distribution, what's partially positive, what's partially negative. It describes magnetism, so paramagnetic or diamagnetic. It doesn't, it's not easy to use, is basically what you should know. You kind of need a computer to be able to find out those things really well. But for our purposes, we're not going to be giving you guys supercomputers to do the molecules, right? Obviously. We're just going to have little diagrams so you can do it. But basically, right here is what's happening in molecular orbital theory. We took two hydrogens, right? And we're bonding them to make H2, okay? And the two orbitals, they can add either constructively or deconstructively to form a sigma, a bonding orbital or an anti-bonding orbital, sigma or sigma star, right? And it makes sense that it's sigma because it's just one orbital. Or I mean, it's just the single bond. Yeah? Anyone have any questions with that? Is that confusing? It is confusing? Everything's confusing? Oh, no, guys. Let's look at the p orbitals next. So this is what happens with p orbitals. They can either add deconstructively, like this one, because the blue and the red are going together. They're not going to like that like magnets. This is going to be anti-bonding because they're out of phase. They want to stay away from each other. They could also add constructively. The red and the red, they're like magnets. They want to go together, and they form a big one, a bond, right? So in molecular orbital theory, what we're talking about is we're talking about sigma and pi mean orbitals instead of bonds. In valence theory, they mean bonds. In molecular orbital theory, they mean orbitals. So you can have bonding or anti-bonding. And we looked at helium, right? We said that if we have helium bonded to another helium, it won't work, right? Because it'll fill up the bonding orbital with the 2 electrons, and then it'll fill up the anti-bonding orbital. And the bond order, we calculated it, it was 0. So it's not gonna stay bonded. There's no bond between the two, yeah. No, but you should understand axes of orbital. What's that? Did you have a question? No? What's up? Yes. So just like shade one side, if it's anti-bonding, shade this far one, and then this close one, or this close one and the far one, and then on the bonding, shade the ones that's connected, or shade the ones, these ones on the outside. Just make sure that it's consistent, right? Yeah. Oh yeah, that's a great question. We're going to talk about that in like a couple slides. But great question. So this is just what I was talking about. They mean different things. Sigma and pi in valence bond, they are bonds. In molecular orbital, they are orbitals, which makes sense. Valence bond, molecular orbital. Okay. This is actually, you know what? I don't know if we're going to talk about what pi bond looks like. And we should talk about what a pi bond looks like in a molecular orbital or just thing. So if we have the 2 atoms and we have the bonding, right? This is the bonding right here. Right? The p orbitals together. This is a p, right? P sigma bonding. And then if we had p pi, these are the same 2 atoms, but if it was a pi orbital and it's a bonding orbital, it would look something like this. Kind of like a hamburger. The same thing, it's above and below. This is bonding. You could also have anti-bonding, which looks like just the same thing, but like with a node in the middle to indicate that it's anti-bonding. Okay, does that make sense? We're going to do some practice with the diagrams in a minute. But basically, you want to know that the the bonding orbitals are way lower in energy, so they're gonna fill up first, right? And then after that, the anti-bonding orbitals fill up too. So when the bonding orbitals fill up with electrons, the bond becomes strong. But when there's more electrons and the anti-bonding orbital starts to fill up, the bond starts weakening and weakening until it's broken when the anti-bonding orbital is full. Okay? Any questions? Okay, let's go on. You should just know this. We talked about this a little bit, but it's important to know. I didn't know it, but it's good to know. I mean, I did know it, but I didn't know it when I took the exam, and it would have been helpful. So yeah, I'm gonna send out the slides so you can just study this on the slides. You can take a picture, or you can just like blink and try to preserve your memory. I don't know, be a little weird. And then I had some other charts. These are just all the same things, just said differently, but it's all the same. You know what I mean? Okay. Let's do a molecular orbital practice problem. So work with your friends or whatever you want on this practice. Raise your hand and I can come to you if you need help. Oh, yeah, sorry guys. This is F2 plus. So it looks like this. Okay, who still needs more time? Are we pretty good? 1 minute? Okay, I'll give you like 1 minute. Okay, it's been about a minute. Let's go over this problem. Okay. So how did you guys approach this problem? What was the first thing you did? Someone yell it out. Electrons. Thank you. I heard it in various spots. So we're going to count the electrons. How many electrons does F2 plus have? How many valence electrons? Sorry, we should specify. 13. Are we sure? Yes, we're sure. How did we get 13? 14 minus 1. Some complex math here, guys. So 14 minus 1, we got 13. And then what did we do from there? Someone tell me. Fill the orbitals. Do I fill them from the top? Why do I fill them from the bottom? Lower energy. Right. What is that principle called? Can anyone tell me? Aufbau. Yeah. It's the Aufbau principle. And you remember that from last time. So we take 1, we put it here, 1, 2, 1, 2, 1, 2. And we're 6. And we do 7. And we come to the other one, we do 8. And then we come to this one, we go 9, we go 10. We go 11 here, and then on this other one, we do 12. We go back to this other one, we do 13. And we're doing the back and forth thing because of, someone say it? Hund's rule. Exactly. We fill them up singly first and then come back and fill them up doubly. So now that we have this all full, I wish I could like write on it, but I can't. So just imagine in your mind. What is the bond order? 1.5. How did you find out 1.5? Right. So I heard a lot of people say it. So you do the number of bonding. So you do the number of bonding electrons. So you do, there's 2 here. There's 2 in this one, this is bonding. There's 2 in this one, this is bonding. And there's 4 in this one. So 2 plus 2 plus 4, that's 8. So we do 8 minus, this is anti-bonding, the star. So there's 2 here, and there's 3 here. 8 minus 5, you have 3 divided by 2. That's a bond order of 1.5. Did that make sense? Okay, we're chilling. Does anyone have any questions? Move on. Actually, wait, is it diamagnetic or paramagnetic? Paramagnetic, because that means unpaired. Diamagnetic means, dang, that's paired. That's how I remember it. Okay. Yeah. Yes, yeah. You mean if you had 1 here and 1 here? Yeah, because those would be unpaired in their orbitals. I forgot to ask you guys, which one is the HOMO and which one's the LUMO? Yell it out. Which one's the HOMO? Yes. Which one is the LUMO? Sigma star 2p. Yeah. Wait. This one's only half full. Is that the LUMO? No, it's not the LUMO because it's full a little bit. So, and it has to be completely not full. So this is the LUMO up here, and this is the HOMO, right? HOMO stands for highest occupied molecular orbital. This is the highest occupied. This is the lowest unoccupied. Okay, yeah. What? No, the HOMO doesn't have to be completely full. And in this case, it's not, right? We have 3 here. I wish I could fill it out, but I have no way of interacting with the slides right now. So, but this one has 3. You should have done it on your papers if you did it on your papers. So this is the highest occupied. This is the lowest unoccupied because it's not that. I saw, yeah. This one? Yeah. No, this would still be the HOMO. This would still be the LUMO up here. The whole level has to be empty for it to be the LUMO. Did everyone hear that? That was a great question. Yeah, the whole level has to be empty for it to be the LUMO. Okay, awesome. And F2 is, yeah, Isaac. There's usually, yeah, there can. It usually is. Well, yeah. Well, unless you had one electron up here. But you usually do have a HOMO on the one. You always, for this class, have a HOMO. Okay, let's move on. Yeah, sorry. On F2? On number 5? Yeah, so you have a HOMO still. So F2, you'd have one more electron. So instead of having 3 here, you'd have 4. Both of these would be full. This would still be your HOMO, right? Because it's the highest occupied one. Yeah, yeah. This would still be the LUMO, right? This one up here, this would be the LUMO. This would still be the HOMO. The only thing that differs in F2 is the bond order. It's just a normal bond order of 1, right? Because it's 8 minus 6 divided by 2, 1. Okay. Guys, does bond order make sense, how we're calculating it? Yes. Okay, good. And it's diamagnetic, F2. Okay, let's go on. That was the first part. Next part, we're going to talk about representations as models, which just means like Lewis structures and like polarity and like all the stuff that we've been talking about. Okay, first thing, let's talk about bond length and bond strength. If I have a single bond, is it longer or shorter than a double bond? Longer. Is it stronger or weaker? Weaker, right, I have it up here. So single bonds are long and weak. Double bonds are shorter than single bonds and stronger. And triple bonds are even shorter and even stronger. So it's like if you break a pencil in half, it's harder to break the next half in half. You know what I mean? So the shorter it gets, the stronger it is. Okay, we good with that? Awesome. What's up? The strongest and weakest bond? I would say that the sigma 2p would be, well, actually the sigma 2s would be the strongest bond. I don't know. I'm not sure. What did you talk about in recitation? Where'd you go? I lost you. You don't know? Yeah, I don't know either. Oh, gotcha. Okay. Just look at the bond order. Whichever one has a higher bond order, that's the one with a stronger bond. Yeah. Okay. Let's go back. We're all good with this, bond length and bond strength. This is important. Good stuff. Okay, Lewis structures, you should be pros. Does anyone need a refresher on Lewis structures? No, okay, good. That's what I like to hear. So these are the steps. You've used these your whole time. Hopefully you should be pros by now. If you're not, say a prayer. I don't know. Let's do some practice problems. Do 1 or 2 or 3 or however many you want of these. And then we're going to come back in a minute and we're going to compare. Okay, guys, I need 5 people to come up and each do one. Come on up. Come on, guys. Grab a piece of chalk. Choose one. I need 2 more people. Which ones are you guys gonna do? Oh, Luke. Okay, O3 and NH4. We need ClF3. Who wants to do it? Luke does. Come on, ClF3. ClF3. 2 more people. 2 more people. Don't be shy. Guys, you're leaving me hanging here. Thank you. Do the first one. You want to do HCO3 minus on the board? No.
I don't know.
I'll say if it's right or not. Which one is it?
Something's wrong here. I counted something wrong. I'm like way over. 0,
Oh,
4, 6, 8, 9, 12, 14, 16, 18, 20, 22, 24, 25.
right.
So I'm
So
like way off.
yeah. So go draw it up on the board, but have the H bonded to one of the O's, and do the C as trigonoplanar, just connected to 3 O's.
How do you know it's
Because I've seen it a lot. Because I've seen it a lot. Yeah, you just kind of have to see it. Yeah. Thank you. I appreciate it. You guys are heroes. I appreciate you. There's the camera. You're on the recording now. Pretty much famous. Okay, guys, I'm gonna turn on the lights. It's gonna get bright, okay? Well, that wasn't that bad. Okay. Hopefully you can see the chalkboard a little better now. I didn't look if these were right, but they look right. This is right. That's right. That's right. That's right. Good job. Good work. And that's right. They're right. Does anyone? Oh, I'm so proud of you guys. So proud. Yeah. This one? On this? Okay, what'd you get? That's good. Yeah. The one on both sides? It actually would have formal charges. It would have 2 plus on this oxygen. Oh, well, that's just too many. That goes over the octet rule. 18? Yeah, what's up? Yeah. Because this is the carbonate is a polyatomic ion, and so it's not going to change the polyatomic ion structure just because of an H. You know what I mean? Also because O is a lot more electronegative, and so the H is going to go to the O a lot more of the time. Does that make sense? Yeah. Any more questions? You did a great job. They just wanted to see it again. Yeah. Do both. So you should do both. Whenever you're drawing loose structures, always do formal charge. And you guys know how to calculate formal charge, right? And then do the brackets. And do the total formal charge here, which is 0. Okay, are we good with that? We're good with that. We're chilling. Okay, any other questions about Lewis structures before we move on? Okay, let's move on. Get rid of this. Oh boy, you can't see it. Okay, guys, we're gonna take a break for a minute. but I'm gonna just to let our brains rest. But I have art prepared for you in the highest form, a dad joke. Okay. So a bear walks into a bar and he sits down and he says, "I'd like a whiskey and a Coke." And the bartender looks at him and he goes, "Why the big pause?" And the bear says, "I don't know. I was born with them." Thank you. Thank you. Quality dad joke. You guys can take a break, like just let your brains rest for a couple minutes before we keep going. Okay, guys, are we ready to start chemistry again? Yeah, chemistry. Woo! Guys, isn't this your favorite Chemistry 105 class that you've ever taken this semester? Okay, is everyone ready again? I'm gonna start. So prepare your chemistry minds, let the juices flow, and let's get back into Lewis structures. So this is resonance. You should know the definition of resonance. It's not, I've drawn this here. This is my drawing. Thank you, I'm very good. So it's the resonance structure is not just swapping between these two. It's actually an average, right? So it's an average of these two. And you use the dotted lines to represent that. So if it says give all of the resonance structures and draw the resonance hybrid, you're gonna do exactly this. You're gonna draw one, and you're gonna do a double-headed arrow, draw another, making sure that you're indicating formal charges where you can or where you need to. And then once you're done drawing all of them, you put them in brackets, put the total formal charge out here. I didn't do that, but I'm bad, so be better than me. And then do the resonance, which is just the average of all of them. Yeah. Totally can. Yeah. As long as it's a dotted line, you're getting points. You know what I mean? Don't worry, just dotted line. Just to indicate that it's a partial bond. Yeah. Yep. Great question. Yeah. Are those what? Yeah, they are. So this just indicates a partial charge. And I don't actually know if you need to be able to do this. I did it because I was like, maybe. But this just indicates partial, right? Because on both of these, this is positive, so it's positive down here. On this one, this is full negative. This one, this is full negative. So on this one, they're half negative, question mark? Not question mark. I mean, I know they are, but like, yeah, that's why I did the partial thing. Yeah, what's up? I don't think so. I think on those questions, it will say draw all the resonance structures. But you should, just to be sure, you should draw the resonance structure that contributes most to the molecule, right? Just to make sure that you are getting it right. Was there a question? Yeah. Yeah, I would say it's the average of all of the resonance structures. Now, I would also know the phrase, the electrons are delocalized. So know those two things because the electrons are delocalized throughout the entire thing. But it is also an average of all the resonance. Yeah. I'm sorry, could you say it again? Oh, yeah. I think. Does that make sense? Did yes make sense to that question? No? Yeah. I don't know. Just draw the charge. I don't know if you're going to have to do this partial thing. Have you done it on your homeworks or is this new? No? Okay, don't worry about it then. Don't worry about it. If you have to draw a resonance, don't worry about it. Okay, we're chilling. Let's move on. These are just some guidelines. You can go over this if you want. But just when you're doing resonance structures, follow all the rules. An important thing in resonance structures is that the atoms don't move at all. Don't move the atoms, just move the electrons. If you start moving atoms, you're doing it wrong. And also, when you're doing resonance structures, each resonance structure has the same charge. Okay? So you can't have resonance structures with different amounts of charge. Does that make sense? You can't have one with a molecular formal charge of -3, while this one has like a molecular formal charge of +3. I don't know how you do that, but you can't do it. Yeah. Right. So it is a resonance structure, but you want the ones that do minimize, maximize bonding and minimize formal charge, because those ones contribute a lot more. And that's the phrase they're going to be using. Contribute a lot more to the resonance hybrid. No, you wouldn't draw the other ones. You would just draw the ones that tie in terms of this. Does that make sense? So if you were just drawing this carbonate, pretend there wasn't an H here. You'd have 2 minuses here, obviously. There would be 3 resonance structures of this. Does that make sense to everybody? Because you'd have one resonance structure where there's a double bond here, one resonance structure where there's a double bond here, and resonance structure where there's a double bond here. You're never going to have a resonance structure where they're all single bonds. This is a positive, and there's 3 negative. Because even though that has the same total net charge of the molecule, it just doesn't contribute. It's not going to work like that. Okay. Oh, also, this is super important. The electronegative atoms are a lot more likely to have the negative charge. So if an atom has to have a negative charge, and you can give it to something that's more electronegative, like oxygen, give it to oxygen. Oxygen loves to be negative. What a jerk. Okay. And this is exactly what we were talking about. So which one do you guys think would contribute most to this resonance structure? These are all resonance, or resonance hybrid. These are all resonance structures. Not all of them contribute the same. So which one contributes the most? C. Why is C? Oxygen is negative. Yeah. This one's neutral. This one's neutral. Oxygen is negative. On this one, oxygen is negative and nitrogen is negative. Or oxygen is neutral and nitrogen is negative. But we could give it to the oxygen, so B is wrong. A is just wrong. Like, Oxygen has a plus charge, this one has 2 minus. If you're doing this, you're struggling. Don't do that one. Okay, any questions? Yeah. Usually yes, because normally fluorine and chlorine are on the outside. They can be on the inside, and when they are on the inside, I would say give them the negative charge, yeah. But usually they're not going to want more than a single bond. Okay. Okay, let's talk about exceptions to the octet rule. We have free radicals. We have incomplete octets, which is basically just boron. And we have expanded octets, which most often is phosphor and sulfur. It could also be most of the noble gases and chlorine. We've seen those before. But those have access to d orbitals. So they can do more. They can have more. You know what I'm talking about? It could be like sp3d2. So, yeah. Makes sense to everybody? Exceptions? You've all seen that? You're chilling? So intelligent. This is the molecular structure. We're looking at it again because you just have to know that you have to memorize this. It's important. The bond angles, steric numbers. Anyone confused about this chart? How to do it? Yeah. Are you confused? Okay. So what you're going to do is we're going to look at E in all of these things. And when we're looking at the geometry, let's say we have a molecule, this one. Let's say we have this one. So what you're going to do is you're going to calculate the steric number around this atom, this chlorine atom, the one in the middle. And steric number is just the number of electron groups around it, right? So there's 1, 2, 3, 4, 5. So we know there's 5. So we go down to 5, steric number. And we see how many lone pairs does it have? It has 1 lone pair, 2 lone pairs. We go down, it's a T shape. Does that make sense? Why it's T shape? Okay. Yeah. Lone pairs are like really negative, really toxic people, and you kind of like run away from those people. The bond angles are small. Okay. I have a question for you guys. If you have a lone pair on trigonal bipyramidal, where is the lone pair going to go? Is it going to go on top? No, it's not going to go on top. Why not? It's not how it works. Yeah, true. It's not going to go on top because that has 90 degrees bond angles with all these three. Where it could be here, they could have 90 degrees with the top and bottom, but like 120 degrees. It's just roomier for it to be there. So that is important to know where to put the lone pairs. So that's good. You guys know. So proud. They grow up so fast. Okay, let's talk about polarity. Who loves polarity? I love polarity. Woohoo. Okay, so these are the polar shapes, or the symmetric shapes, right? So when you're finding polarity, 2 things matter. The polarity of the bonds and the shape of the molecule. It doesn't matter what the polarity of the bonds are if the shape is one of these symmetric shapes, okay? Unless, of course, you have 2 different things. Like if this is a fluorine and this is a hydrogen, even though it's symmetric, the fluorine is way more electronegative, it's polar. Does that make sense? Is everyone understanding what I'm putting down? Yeah. Yeah. It would be pointing towards the hydrogen. So this arrow that we use, let's actually draw that. So I don't know if it'd be a C. Okay, well, it wouldn't be this. This doesn't work normally, but just pretend. Okay. CF, no lone pairs. I don't know. We broke chemistry on this one, but it's linear. Okay, it's linear, and the bond dipole on this one, C to F, is going to point to this way. It's pointing towards the more electronegative one, and this is a little positive sign to say this is electropositive, right? Because if this one's electronegative, just broke my chalk. If this one's electronegative, it's going to be pulling the electrons kind of away from it. This one's going to be electropositive, right? Does that make sense? The plus sign. This one, it's not really polar, non-polar. There's no arrow. So the net dipole is going to be going this way. Okay, we're good? We're chilling? Important thing with polarity, maybe I have it on here. I don't. Important thing, if we have an H3, this is a great one. Everyone understand this wedge in the dashed line? Wedge is coming out at us, dashed line is going behind. This is, someone tell me the shape, geometry. The molecular geometry. Trigonal pyramidal, yeah, or pyramidal, whatever. So yeah, you guys, yeah. I have a question for you guys. Which way is the polarity of the molecule going? Up. Why is it up? Very good, very good. You knew that. What if the hydrogen bonds were chlorine instead? It would go down. And what I'm trying to get at here is this lone pair. This lone pair doesn't contribute to polarity at all. Okay, it's just electrons floating around. There's no electronegativity difference because there's nothing it's bonded to. So that can trip a lot of people up. They see lone pairs and they're like, oh, well, it's polar because it's going that way. Yes. Right. So if these hydrogens were chlorine instead, it would go directly down. The net dipole. The molecular polar bonds or the molecular dipoles would be following the bond. Yeah. What? No, it's not symmetric because this has a lone pair here. On this one, if it had another hydrogen like this, if it was this shape, it would be symmetric. Yeah. Every time it has a lone pair, it's not symmetric. Or yes. Double bonds? Yes, they do. So double bonds, there's more. If you had O double bonded, C single bonded O, I don't know if that's a real thing, maybe not. This would be more electronegative because this C is basically bonded to the O twice. So this O is pulling on a lot more electrons, so the net dipole is going to be going this way. No. Yes. That would be nonpolar. Right. You got me. You win. You win this round. You win this round. So he had a great question. What's an atom that can do that? I don't know. Xenon. So he said, what if it's sp3d or it has 5? And I don't know what this is. Fluorine? Sure. What if it's like this? Is it gonna be polar even though there's lone pairs? No. Because it's basically linear. Okay. So this what? Who said what? It's linear. Does that make sense? Okay, linear. And we can go back, like we can look at the chart. Right here, we see that this one, 3 lone pairs, it's linear. Linear, linear. And because it's linear and they're both pulling in the same way, non-polar. Unless the atoms bonded to this are different. If the atoms bonded to this are different, it is now polar. Okay? Are we good with polarity? I want to move on. Okay, we're good. We're good with polarity. Talk about naming stuff. What's in a name? Okay, guys, I hate to break it to you. You just gotta know it. I know, it's the worst. There are Quizlets. If you don't know it, you're screwed. to put it lightly. So memorize. Not much else I could say. I can't really soften the blow that much. Okay, good luck with that. I don't know. Good luck. Does everyone know where to find this chart? Okay, we're good. All right, let's go. Okay, so when we talk about nomenclature, which just is a fancy way of saying naming crap, we're going to be set first. We have to decide what it is we're naming. Okay, so we can either name ionic compounds, acids, or covalent compounds. Right? Okay, and they all have different rules. So first, let's look at ionic, right? The rules for naming ionic compounds. Let me see if I can read it. So first, you're going to name the cation, and then you're going to name the anion, and that's it. Okay. If you're given, let's say, you know that your ionic compound has magnesium and it has fluoride. The way you're going to find out what it is by putting them together until they have neutral charge, right? So 1 Mg has a 2+, 1 F has a 1-. You want to make it neutral, so you have 1 Mg, 2 F-. Yeah, we good with that? Solid. So F or MgF2, what would the name of it be? Someone yell it out. Magnesium fluoride. Really easy. You just name the cation, just say the name of the cation, which is the positive one. Usually it's over here. And then you name the what's it called? Anion, but you put "ide" at the end. You could have magnesium oxide or sodium sulfide. It's easy. Easy mode. You got this. Ionic compounds, those are the best ones. Oh yeah, this last one, for transition metals, anything in here? You're gonna see Roman numerals, and you should be able to do the Roman numerals now. Roman numerals just mean the charge of the cation. So this is Fe3. Yeah, what's up? Why are they exceptional? I mean, maybe they are. I don't know. Oh, okay. I don't know. Yeah, maybe. Sorry, that's really disappointing. I don't know. I'm human, I guess. My bad. I'm sorry. I wish I knew. I'll learn. I'll Google afterwards. I'll study for you. Okay, any other questions with ionic compounds? Yes. Transition metals are cations. Yes. Okay. Let's do some practice. So I want you guys to do the first 3 of this column, and then the first 3 of this column. We don't have time to do all of them because we're going to do similar things for covalent and acids. But name the first 3 on both columns. Ready, set, go. Okay, guys, who needs more time? Okay, we'll do 30 seconds. 30, 29. Okay. All right, someone shout at me the answers. What is on this first column? What are the first three? Potassium sulfide, what's the next one? Barium chloride, what's the next one? Magnesium phosphide, very good. Can someone tell me the formula for aluminum oxide? Okay, this is very good. Good job, guys. This one, I blame Dr. Sansom because aluminum should have probably Roman numerals on it. But also, maybe it shouldn't because it always has a +3 charge. It always has +3 charge, aluminum. So it doesn't have, even though it's a transition metal, aluminum always has +3 charge. And you can tell that just by that periodic table. Okay, so very good on that one, Al2O3. What's the formula for magnesium fluoride? What? MgF2. Oh, that's right. I already gave it to you. My bad. Okay. What about potassium nitride? A3N. Don't get confused. Don't think it's potassium nitrate or nitrite. It's nitride. If it was potassium nitrite, it's said on the formula, that'd be very different. Okay. That would be KNO2. Yeah. Okay. Good. KNO2. But it's not that, it's potassium nitride, so it's K3N. Any questions about ionic compounds? This is the easy one. I mean, you can still have a question if it's easy. Just gonna judge you. Just kidding. Okay, let's talk about covalent compounds. So these are the rules. Rules. Ooh, cool. You're gonna put the less electronegative atom first. Okay, when you're dealing with covalent compounds. You're going to use the Greek prefixes, which you've learned, we've talked about. There's mono, di, tri, tetra, penta, hexa, hepta, and you don't have to go about hepta, really. But you could do deca, you could do nona, I don't know. But you're going to use those, and this is the pattern you're going to use. You're going to do prefix, element, space, prefix, element, ide. Okay. So let's say we had, this one here is good. We have the prefix of the first one, di, because there's 2 phosphorus. So di, phosphorus, space, prefix element ide. So prefix is tetra, but it's edited down to tetra because oxide starts with a vowel. So we have prefix, element, and then ide. We kind of cut off the element and just throw ide in there. We good with that, how it works? Solid? Okay. Another thing is don't use mono when naming the first element. Just get rid of it. That's why this is in parentheses. You don't do like, what's something? CO2. You don't do monocarbon dioxide. You just do carbon dioxide, right? And then the last thing is prefixes ending with vowels. Those are modified a little bit when used with elements beginning with vowels. So just make sure that when you're given a formula, you have to write out the name. If the prefix and the element, both, if the prefix ends with a vowel and the element starts with a vowel, edit it to make sense. Okay, we're good. Are we good? Who's good? We're all good. We're great. We're all good. And you saw that it was good. Let's do some practice. Do the first 3 on both sides again. Ready, set, go. Okay, guys. What is the first one on the formula name? Carbon dioxide. Very good. What's the second one? Carbon monoxide. We had to do a little editing because mono ends with O, oxide it starts with O. You just smash them together. What's the third one? Diphosphorus pentoxide. Someone over there is very smart. Good job. You're all smart, but okay. What is the formula of this one? NO, no. I mean, yes, but it spells no. What is the formula on this one? N2O. What is the formula on this one? NO2, kind of swippy, swappy, weird stuff. Okay, does anyone have any questions on covalent compounds before we move on? Who has questions? Anyone have questions? We're good? No questions? We're chilling. Let's move on. So next we have acids. So you guys covered this in class, I think. Hopefully, I wasn't there. I was skiing. So, but I learned about it already. So, okay, let's talk about acids. So there's two different types of acids. There's binary acids, which just means two different acids or two different elements in the acid. And you have oxo acids. There's different rules for both. So in binary acids, it contains a proton, H+, which is just a proton, and one other element, or cyanide, which is just Cn. And you should know that from the table. So we can have hydrofluoric acid if it's HCl. If it's H2S, it's going to be hydrosulfuric acid. If it's HI, it's going to be hydroiodic acid. If it's HBr, it's going to be hydrobromic acid. HCN is hydrocyanic acid. The cyanide can be a binary acid too. Oxo acids are when it has an oxygen in there. Usually it's oxygen, but it's called oxo acid. And it's basically a hydrogen with a polyatomic ion. Okay, before we do oxo acids, are there any questions about binary acids? Okay, let's talk about oxo acids. It's generally a hydrogen and a polyatomic ion. And this one, you're going to balance the charges to find the formula. Does that make sense when I said balance charges to find the formula? Yes. Okay, no? Okay, so let's say we have let's say we had sulfuric acid. Okay, pretend like this isn't here. H2SO4. What you know, and we're going to talk about this in a minute, is ic means 8. If you have an acid that ends with ic, the polyatomic ion ends in 8, so it's a sulfate. Okay, so we're going to draw our sulfate. I always lose my chalk. Okay. So we're going to draw our sulfate. And then we know this has a charge of -2, right? Because we've just drawn it out. Makes sense. -2, there's a -1 here, -1 here. Okay? And if it says sulfuric acid, and we know it's ic, so it's sulfate, there has to be 2 hydrogens to balance that charge out. Does that make sense what we did? Everyone understanding? Okay, let's talk a little bit more about that. You're going to name your acid based on your polyatomic ion, okay? They're playing chess here. Okay, so if it's a sulfate group, it's going to be ic, so sulfuric acid, this is sulfate. If it's an ite polyatomic ion, it's going to be us, so nitrous acid, this is a nitrite. And what helps me remember is I ate it and it was icky. I took a bite and it was delicious. It's just a little mnemonic to help me remember. It doesn't make sense at all. Like, it doesn't make sense, but it helps you remember if you memorize it. Ate, ick. Ite, delicious. Right? Okay, does that make sense? So that's what we're going to do with these oxo acids. That's how we're going to name them. Does anyone have questions about oxo acids or just any acids in general? Or for LSD? Okay, move on. So let's practice these ones. Let's do the first three of each column and not play chess. Okay, who needs more time? Does anyone need more time? Okay, I'll give you like 30 seconds more. Speed run, ready, set, go. Okay, that was probably like around 30 seconds, maybe. We don't have a ton of time left. We're gonna end at 8 so that it doesn't, we have 20 minutes left. Yeah, what's up? You're confused about the HCl and the HClO3? So HCl is hydrochloric acid because it's a binary acid. Yes, it is. And HClO3 is chloric acid. Does that make sense why it's chloric acid? If it was chlorous acid, what would it be? Someone tell me. H2ClO2. Yeah, you're right. Thank you. What's up? If it was HClO, I think it would be perchlorous or hypochlorous acid. I think is what it would be, right? Does that make sense? I think that's right. I don't know if you're gonna have to do something like that. But I would just give it a quick Google, maybe ask ChatGPT. Okay, guys, bring it back in. Let's focus. Let's focus now. What is the answer? What is the formula for this one right here? HBr, that was easy. What about this one? HCN, yes. What about this one? HNO3, right? Because it's a nitrate, right? Because it's nitric, that means it's nitrate, which is NO3 minus. So we throw one H on there, HNO3. Okay, we're chilling. Let's move on from nomenclature. Guys, I have up here, if you're gonna download the slides and you're still confused about this, you can look at this flowchart. It looks really confusing. I promise it's just exactly what we just did. So you can just look at this flowchart if you're gonna download the slides. Okay. Let's move on. This is another flowchart. I don't know, they were on the textbook. I was like, why not? I'll add them. Okay, you're good. Okay, guys, we're almost done. This is the last thing we're gonna talk about. I think so. We got 20 minutes. Let's bust this out. You're gonna be experts at the end. Okay. So these are all the, what are they called? Functional groups that you have to memorize. Guys, you just got to memorize a lot of stuff for this exam. The polyatomic ions, you got to memorize the functional groups. You got to memorize the shapes and the angles. Lots of stuff. But you can do it, I believe. Yes, what's up? There is a lot more. I would just memorize these because these are just screenshots of the slides in class. So if she tests you on something that wasn't on the slides in class, that's just lame. I don't know. I don't know what to tell you. So this is an alkane, right? Alkene, alkyne. This is the benzene ring. We just have functional groups right here. If you guys are confused about functional groups, organic chemistry tutor, just type in functional groups on YouTube. You get like some Khan Academy stuff or I don't know, something. You got to memorize all of that. All of that. I would memorize, yeah. Okay. Good luck with that, guys. Good luck. Yes, sorry. I'm sorry, what? Is it a straight line? Because it'll never be like that. Because these carbons, what is the hybridization on these carbons? What? sp3? No. That's a great try, but they're sp. Yeah. Okay, that was a good question. Did everyone understand that? She's asking why this one is linear. And I said, well, this carbon here and this carbon here, these are sp, which means they're going to be linear, right? Okay. So this is an alkane. We have alkene. We have alkyne. This is a benzene ring. And just memorize those. Let's do some practice. Okay? Yes. It depends. It's only a benzene if it has these three, like that. If it is just a ring and it's got like maybe one double bond, that's not a benzene ring. You don't say it's anything. Just, it is what it is. It just be. It just do what it do. Okay, guys. Let's do a practice problem, but do it in your head first. It seems intimidating. It's not. You can do this. So everyone, quiet. Let's be calm and peaceful. So in your own head, without talking to your neighbors, try to go through and figure out what all of the functional groups that you can recognize in this molecule are. If you can do something like this, you can do anything on the exam. Do in your heads, do in your heads. Okay, guys, has everyone had a little bit to go over it? Okay, I'm gonna go over it, and yeah, okay. So the functional groups that I see an alcohol here, an alcohol here, an alcohol here, an alcohol here, and an alcohol here, right? Alcohols are just OH. So I see like 1, 2, 3, 4, 5 alcohols. I see this. What is this? Can anyone tell me what this is? No, you can't. An amide. Yeah. This is an amide. Because this is R, right? This right here, the whole rest of the molecule is R. Okay, this is an amide. This is, what is this? Can anyone tell me? Amine, yes, this is an amine. There's one more functional group that I see. Oh, okay, you're right. Okay, I actually see 3 more functional groups. So yes, there's a benzene ring right here. And someone said it, what are the other 2 functional groups and where are they? We have 2 ketones right here. This is a ketone. And this is a ketone. This isn't carboxylic acid because if it was, there would be an OH right here. But so this is a ketone and this is a ketone. So you guys should know what the functional groups are and how to be able to know the functional groups, look at a molecule, and be able to know where they are. Okay? Oh boy, lots of questions. Yeah. Yes. Yeah. Yeah. So on this ketone, for example, this ketone, you would circle right here where my laser's going. Oh boy, I'm bad. Like through that bond, you'd circle right there. Good circle. On this amide, you'd circle right here. Okay. This benzene ring? Yeah. So you don't actually consider the carbon in the alcohol. It's just OH and then anything else. So you just circle the OH. Okay. It's only in some of them. Yeah, it's only in the functional groups with a carbon that you use the carbon. Yeah. No, this is just an alcohol because it would only be carboxylic acid if the OH was right here, directly connected to this C that the O is double bonded to. But it's not, right? This is connected, this alcohol is connected to this carbon. And yeah, but that was a great question. Any more questions? Yeah. Oh yeah, yeah. So I did miss 2 alkenes. So you have an alkene right here and an alkene right here. Thank you for that. Alkenes are just double bonds. Alkanes are single bonds. Don't worry about alkanes because there's alkanes literally everywhere. But alkynes are triple bonds. Okay, we're gonna move on because people are tired. We've been here for 2 hours. Let's finish up strong. What are the functional groups in this one? Someone yell them out. Oh boy, is it an alcohol? It's a carboxylic acid, yeah. We have a benzene ring and an ester. Okay, let's move on from functional groups. Guys, this is important too. We have this, and then we're going to talk about isomers. So give me your attention for like 10 minutes, and then you could talk all you want, okay? So something important that we're going to talk about is oxidation. And you should know what oxidation is. You should know what functional groups are similar to each other and which ones have the same amount of oxidation. So here we have an alkane. If we break a CH bond and form a CO bond, so take off, let's say this has 3 H's on it, right? 3 implicit H's that we can't see on this carbon. If we break one of those and form an O bond, a CO bond, that's an alcohol. If we do that again, that's an aldehyde, right? If we do that again, that's a carboxylic acid. So the oxidation is just the number of CO bonds that you have. It goes up with the number of CO bonds that you have. Okay, does that make sense? Okay, and the reason you should know this is because it has different, oh boy, I didn't put it in. Just know this. Yeah, good. Okay, we're gonna talk about isomers, and this is the last thing. And then we're done. I know. We're almost there, guys. So isomers are molecules with the same chemical formula, but in a different structural arrangement. Okay? Different structures. You can have a structural isomer, which is like you could have something like this, right? Or you could have something like this. Those are structural isomers. Does that make sense to everyone? Yes, okay, good. You could have stereoisomers, which is same connectivity, different arrangement in space. The ones we talked about were cis and trans, which you should know how to do pretty good. It's not, I mean, cis and trans is not that hard. Is this cis or trans that I've just drawn? Cis, yes, it's cis. What if I drew it's trans, yeah, that was a wild guess. So these are geometric isomers, cis and trans. The last thing that you can have is optical isomers. And optical isomers have chiral centers, or the chiral carbons. Chiral carbons are carbons that are sp3 hybridized, so carbons with 4 things attached to it, and all the 4 things are different. If it's the same thing, if any of the things are the same on that carbon, it's not a chiral carbon. There has to be 4 things, and the 4 things have to be different, and that makes it a chiral carbon. This is just a flow chart. It says exactly what I just said, what we just went through. You can have enantiomers or diastereomers. Don't really worry about diastereomers. Those are both optical isomers. This is also the same thing. Okay, let's do practice problems for the isomers, and then we're done. So this is very high quality, as you can tell. So let's see what you guys come up with. Okay, guys, how would you do this problem? Count your C's and H's. Yeah. So what you're gonna do on this one is you're gonna go through each molecule and you're gonna count all the C's and all the H's. And basically, you're just gonna find the molecular formula or the chemical formula for those 4 compounds. Whichever ones are the same, those are structural isomers. If they're different at all, they're not structural isomers, they're just different molecules. So what's the answer? Does anyone know? C? Which one? Only C. I don't know. I didn't do the problem. It was a lot. Is it C? Someone tell me. And D? C and D? We should have a work. I think we should divide up into two sides. I don't really know the answer because I didn't want to do it. I know how to do it. Okay, we all know how to do it. You just count out, you find them like in the formulas, and you're good. What? War is fun? I don't know. Yes. Totally fine. That's totally fine. Well, I don't know if it's a structural isomer or not, but if it had the same formula, then yes. Yeah. Yeah. What? Hydrogen also be added to the OHs? No, because you count the hydrogen into the hydrogen count of the total molecule. So that just counts for the hydrogen total. You're gonna find the total number of carbons, which is 1, 2, 3, 4, 5, 6, 7. C7, I don't want to count the number of H's, but that goes into it. O, right? And all of them have an O, so we can't just determine it with O. We'd have to count all the C's and the H's. That makes sense, right? Did that make sense? This is another problem. Let's not do it. Good luck. Great job, guys. Thank you. You've got this. Study hard. I believe in you. If you have questions, you can come up. If you want to leave, get out of here.